Alright, let's get started with lesson 1 on electromagnetic waves. This is a really important lesson, so please take careful notes, and if you need to, re-watch this video. This will give us a good introduction on quantum mechanics. We're going to start out with this lesson on looking at waves, specifically on a special wave called a standing wave. Now, all waves are generated due to the motion or movement of matter, in particularly the vibrational motion of matter. Now, because all matter has kinetic energy, it allows for matter to move and creates these kind of waves. Now, an important type of wave for us are known as standing waves. Now, standing waves are generated because there is matter that is connected to two fixed ends. For example, we have a rope here, and this rope is going to be connected to two fixed ends. One is a wall, and the other is a hand here. Now, as the hand moves up and down, it's going to transfer some of its kinetic energy to the rope, and this will allow the rope to also move up and down in a vibrational motion. And when it does so, the rope is going to generate a wave. Now, you can see in this first picture, A, that we're going to only generate one wave, which you can see by one wave peak and one wave trough. All right. In the second picture, we see two waves being generated, 1, 2, and we have two crests and two troughs. In the middle of those two waves is a region called the node. All right, we will begin to talk about nodes a little later, but just to make sure you understand, nodes are created in between two waves, or in between two wave crests. The last picture, we create three waves here. Each of them have three wave crests, or three peaks, and in between those wave peaks or crests, we have two nodes, a node here and a node there. Okay, so just be kind of familiar with that idea. Now, a good example of producing standing waves is a guitar. A guitar string is fixed to two locations or 2 points, and as someone begins to play a guitar or pluck the guitar string, it begins to generate vibrational motion of the string, which then results in a standing wave. And those standing waves, which generate energy themselves, will radiate out from the guitar and cause air to begin to move. And when air begins to move, then it creates sound. So standing waves are converted into sound waves, which we then interpret as, well, sound. And we can hear music from the guitar. All right? All right. Let's look at some characteristics of all standing waves. As we mentioned earlier, a standing wave contains wave crests or peaks. The top of the peak is called the wave crest, and the bottom peak is known as the wave trough. Now, the important part of this standing wave is to understand some vocabulary words. So the distance from wave crest to wave crest is known as the wave length. We also have the wavelength, which is the distance between trough to trough, and it's the same exact wavelength from crest to crest in a standing wave. Alright, so here's the definition of wavelength. Formally, the distance between two consecutive peaks or troughs in a standing wave. Now, the units for a wavelength are going to be meters or nanometers that we're going to typically use in this class. All right? Now, we use an abbreviation or a symbol for wavelength, which is this funny little character here that we call lambda. Now, that's not a very good one, so let me draw it again. Okay, this is known as lambda. It's a Greek letter. And it just identifies that we're talking about wavelength whenever you see it. And again, the units are in meters. All right, another important characteristic of standing waves is its frequency. Frequency, abbreviated as a mu, which looks like a V, or an F for frequency. All right. Now, by definition, the frequency of a standing wave is the number of wave cycles per second that passes a given point in space. Well, what do we mean by cycle or a wave cycle? Well, that's just simply the number of crests that pass a given point per second. All right? So, for instance, let's just say we have a point in space. And we have a wave. And let's say that two crests, 1, 2, those crests pass that given point in 1 second. So that would mean that we have 2 cycles, or the standing wave creates 2 cycles per second, or 2 wave cycles per second. All right? Now, the way we write or use units of frequency is either cycles per second, which is 1 over a second, or hertz. So let me explain this. Let me show you. Let's go to a whiteboard. I'm going to kind of show you how this would work. All right? So let's say we got a wave. Here's our point in space that we're going to count the number of crests that pass a given second. So here's a wave here, boom. And we're going to say that there are 1, 2, 3, 4 crests that pass this point right there in 1 second. Okay? So the frequency for this wave would be 5 cycles per second, or what we'd say is seconds over 1, because 1 over a second is equal to seconds minus 1. Okay, take the reciprocal of that. And so that's commonly how we'll write that, is 5 cycles per second. Well, in other words, there are 5 crests that pass that given point in a second. Or sometimes we'll write it as hertz. So we'll say 5 hertz. Hertz is equal to a cycle per second. So oftentimes we'll see it written as hertz. Okay? So that's one example. Let's do another example here. Let's say we have another wave. All right? And we're going to count how many crests pass that point in 1 second. And let's just say we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 crests that pass this given point in 1 second. So our frequency, which again, remember, is an F, is equal to, we said 8, so 8 cycles per second, or 8 hertz. Okay? And so that's basically how we determine the frequency, is just the number of wave crests that pass a given point in exactly 1 second. Right, if you're having trouble with this concept, come and see me before you take the quiz, and we'll discuss it some more. Okay? All right, so let's go back to now amplitude, our definition. Now, amplitude is our final characteristic we want to talk about. It simply is the amplitude is the vertical distance from the midline of a wave to the peak or trough, and is related to the wave intensity. The higher the amplitude, the more intense the wave will be, the more intensity it has. Also, the higher the amplitude, the brighter the wave is in terms of light. So when we're looking at the brightness of light, which light is a wave, so when we're looking at how bright it is, the higher the amplitude, the brighter the light that we're going to see. All right, so here we go. To summarize this whole thing in a nutshell, we have wavelengths, which is the distance between crest to crest. We have frequency, which is the number of peaks that pass a given point in 1 second. So in this case, we have 2 peaks that are passing a point in 1 second. So we're going to call this a frequency of 2 cycles per second, or, oops, wrote that wrong, 2 cycles per second, or 2 hertz. Alright? We also have amplitude here. Amplitude is the height of the wave from crest to crest, or height of the wave from the midpoint to the top of the crest, or from the midpoint to the trough. Alright? Alright, now, we are now going to finish up this lecture video with talking about a very important type of standing wave known as electromagnetic waves. So, electromagnetic waves are produced by the vibrational motion of electrically charged particles. You absolutely need to understand that. Now remember that all waves are generated by the vibrational movement of matter. But when we have a charged particle that's moving in vibrational motion, then it creates a very special type of standing wave known as an electromagnetic wave. Now these waves are also called electromagnetic radiation because they radiate from an electrically charged particle. Now all matter contains charged particles. You know that because all matter is composed of atoms. They're going to have protons and electrons, which are charged particles. So therefore, all matter is going to be moving or have charged particles that are going to move, and therefore all matter radiates electromagnetic waves. A vibrating charged particle creates two types of waves. One is an electric field, which is really an electrical wave, which produces then another wave, which is a charged magnetic field that is perpendicular to it. So what I'm saying here is that when you have a charged particle and it's vibrating, it's going to produce two waves that are perpendicular to it. One is an electrical wave and the other is a magnetic wave. And these two waves are going to travel together as one electrical magnetic wave. So here's a diagram that's in your notes here. We'll kind of look at of an electromagnetic wave. So what we have is a charged particle here, and this charged particle is moving up and down in a vibrational motion. Right? Because of that, it's going to create, let me draw this, it's going to create an electrical wave, like so, and it's going to create a second wave, which is a magnetic wave, and it is perpendicular to the electrical wave. But both waves are moving in the same direction, away from the charged particle as it's vibrating. Alright? Alright, so EM waves. Now EM waves is just an abbreviation for an electrical magnetic wave. So an EM wave travels through empty space as well as through air and other substances. All electrical magnetic waves travel at the same speed through a vacuum, which is 3.00 times 10 to the 8th meters per second. This is known as the speed of light, and it's very important that you learn the value of the speed of light. Now, this should give us a clue about the nature of electromagnetic waves. Another name for electrical magnetic waves in common terms is light. That's right. Now, all charged particles that are in vibrational motion are going to emit light then. And this light is really an electrical magnetic wave that radiates out from those charged particles. Alright, so we're going to finish up this lecture video by looking at some characteristics and summarizing electrical magnetic waves as a whole. So, we have a charged particle, and that charged particle is going to radiate and move up and down. Let's see, let me erase this, do a little bit better. Okay, so we have a charged particle here, and it moves up and down, vibrates, and as it does so, it's going to emit electromagnetic waves or light. Remember, light is an electrical magnetic wave. It's just that an electromagnetic wave is a more technical term for light. So it's going to create an electrical wave, and it's going to create our magnetic wave that are perpendicular to each other, but they're propagating or moving in the same direction. They both waves have wavelength, and that wavelength is exactly identical to each other. And they both waves have the same frequency and the same amplitude and the same speed, which is the speed of light. So both waves that are perpendicular to each other travel in the same direction at the same time as one complete unit, which we call electrical magnetic waves. Same wavelength, same frequency, same amplitude, same speed, same direction, all radiating out from the same charged electrical particle. All right?